the next section is about increasing, decreasing, and the first derivative test. 4.3. Increasing and decreasing functions. And first derivative test. Right, so before, right, we say function is increasing when it's monotonically getting bigger. Right, such that, well, f of x1 is less than x2, then f of x1 is less than f of x2, such that is when function is getting bigger, the f value is getting bigger, therefore the secant line is getting bigger. Right? Then decreasing if as the x is getting bigger, the y value is getting smaller. As the function is getting bigger, then the f value is getting smaller. Right, then in the view of secant line, we know that, well, f of x2 minus f of x1 over x2 minus x1, if they have same sign, right, which is both, if you subtract, are greater than 0, in this case, is less than 0 and greater than 0 to be positive, that is increase, to be negative, that's decrease. Right, but when we extend it, x2 minus x1 is very close enough that we'll get to a view of tangent line, that in the view we can say, well, f prime of x is positive or f prime of x is negative, that we get an increased function or decreased function from that. Right, that we get x2 minus x1 is bigger than 0 for increase f of x2 minus f of x1 is bigger than 0. Right, and the opposite other words. Right? So when we in the view of secant line for any x2 and x1, we get the difference of quotient basically. It's positive for increased function, it's negative for decreased function. And then in the view of calculus, we approach the difference between x2 and x1 to be close enough to 0, then the difference of quotient will yield to the slope of tangent line, which yields to the derivative. Right? Therefore, the tangent line, which is the slope of tangent line, which is derivative, is positive, and derivative is negative for increase and decrease functions. And that is what we have seen from pre-calculus, and this is what extends to calculus, what it relates to the slope, what is related to, in other words, the derivative. Right, so the first theorem, or the first rule we use, test for increasing and decreasing. If f prime of x is greater than 0, for all x in A to B, then f is increasing on A to B. Right, we have discussed about differentiability on the open interval, therefore it is because also therefore also when we discuss the increasing or decreasing interval is on the open interval. Right, so second, if f prime of x is less than 0 for all x, we could use another notation for all x belongs to A to B. then f is decreasing, on A to B. Alright, so to check decrease, that is, we need to check for the f prime of x, right, to be negative. Then for f prime of x equal to 0, for all x in A to B, then f is constant. Right, that three thing we get derivative is positive, that we get a positive tangent line, that function is increasing in either way of increasing, right? And in either way of decreasing, with curvely or straightly, could be they all are increase or decrease, right? Constant is just a horizontal line. Right. So that is it for the increasing and decreasing test for it. Well, we'll see by example, and the steps to find is find critical numbers, because the critical numbers is possibly the points that change the monotonicity. Right? Therefore, to find the critical numbers will help us to separate the domains, determine the test intervals, and second, determine sign of f prime. At one test value, in each interval. Right, so that is what it is. I determine the sign of f prime at one test value in each interval. Right, so which means the critical value is only the possible way to change the monotonicity. Right? Then determine then the interval will be the entire domain basically. Right? Will be broke by the critical numbers. Then for each interval, it should be monotonic. Then determine the sign for each interval. We just need one test value inside each interval that will get the sign. Then from the sign we are able to determine if the function is increase or decrease at this interval, right, on this interval. Well, basically everything is regarding to the domain, right? So always domain is very important. Right, find the open interval, always, on which f of x equals x to the third minus 3/2 x squared is increasing or decreasing. Right, let's see the full step, right, how to do this type of question. We first of all, actually, right, the steps was missing was the first step to find out the domain. Right, the domain is all real number. since that is a parabola. Then we are able to find the derivative of the function, 3x squared minus 3/2 times 2, which is 3x squared minus 3x. Right, is differentiable everywhere. Right, since the derivative function is defined everywhere. Right, so f is differentiable everywhere, or f prime is defined everywhere, same thing. Right, because the critical value is looking for critical numbers, right? It's looking for where f prime is equal to 0 or f prime is undefined. When we measure f prime is defined everywhere, to find the critical number we just need to solve for f prime equals 0. F prime of x equals 0, that 3x x minus 1 we can factor out. To be x equal to 0 and x equal to 1. Right, then after that we can just, we don't need to find nothing else, so only the increasing and decreasing interval. So we have the intervals which is a cut of our domain, right? The 0 and the 1 are cutted. So negative infinity to 0 is the first interval, 0 to 1 is our second interval, and 1 to infinity is our third interval. And of course, if you know how to solve for the inequalities, you are able to solve for f prime of x greater than 0, f prime of x less than 0 to find the interval of each one. That is the most straightforward way. If you don't know how to solve for the f prime, if you don't know how to solve for the inequalities, then it's better to build a table and use the test value. Right, so test value, we can, for the interval that is between negative infinity and 0, we can use the value of negative 1. Between 0 and 1, we can use 1/2 as the value. Between 1 to infinity, we can use 2. Any value that is convenient will be good enough. If you don't like negative 1, in between negative infinity and 0, you could use negative 2, negative 5, negative 10, all the values is fine. If you don't want 1/2 in between 0 and 1, you can use 1/3, 2/3, or whichever value in between 0 and 1. If you don't like the 2 in between 1 and infinity, you can use any value bigger than 1, Nothing important. Therefore, the sign of f prime will be determined by the next column, and therefore the f has increased or decreased will be clear. Maybe you can write f prime of x, f of x to be true, what that is. So f prime of x, that's 3 times x minus 1. You don't have to show steps. You can write this on your scrap paper. 3 times negative 1 minus 1. That is a positive times negative times another negative number, which is positive. You don't have to write out the value. You can just, because we're only looking for the sign, you can say, well, 3 times negative 1 minus 1, that is positive times a negative times another negative, that yields to a positive number. So it is positive. And for 1/2, that's 3 times 1/2 times 1/2 minus 1. Hence, that is positive times positive. 1/2 minus 1 is a negative, which yields to a negative number, whatever the number is. Then the third one to be 2, that is all positive to be clear to get positive. Right, so that is the thing you can write on square paper. You can just show the conclusion, say what is what for each underneath interval. Then for f of x, that is increase, decrease, and increase. Right, you could just use the arrow to show that increase or decrease. Right, or if you don't want to use the arrow, you can say, well, increase, decrease, and increase. Right, either one is fine. Therefore, now we get conclusion that f of x increases on the interval from negative infinity to 0 and 1 to infinity, decreases on the interval from 0 to 1. Right, that is a full step. To find the derivative, find the critical numbers, then use the test value to build a table for the intervals, to find and dig out the test value out of it, then to find the sign of positive or negative, then finally the conclusion of f of x. Then write a sentence about the monotonicity, right? Increasing on the certain interval and decreasing on certain interval. Right? Try not to use union, just use the comma and. Since we break interval nicely, let's separate all of them, right, to be more separately expected. That is one example we have seen. And the first derivative, for that also we're going to use is the idea of increasing and decreasing interval. So we will have a practice still. So let's jump to the first derivative test. The first derivative test is testing for relative extrema to be specified. Right? The derivative test is always testing for the extrema. And it doesn't just say, well, the derivative test, which means we use the first derivative SN8 to find the extrema. Later on, we will have seen something using second derivative SN8 to find the extrema, which is called the second derivative test. But first of all, that's the first derivative test. So let C be a critical number. Right, the first thing is if prime of x changes from negative to positive, let's see. Then f has a relative minimum at the point C f of c. Right, for instance, the function is c is a critical number, that's the derivative equals 0 or derivative is not exist, right? But the function is at c left to it is decreasing, and after the c is increasing. Decrease to increase at the c value, then the c will be the relative minimum. Right, the c is relative minimum. That we had brief introduction in our section 4.1, which here is the fully description of what it is. Right? F prime changes from negative to positive, which means f is changed from decrease to increase, no matter how the critical number looks like. Right? Maybe horizontal tangent line, maybe the is not applied, right? Maybe f prime is undefined at the c. Both way that we get is the relative minimum, as long as the f prime changes from negative to positive. Right, the second saying, well, if the f prime of x change from positive to negative at the value c, then f has a relative minimum, a maximum at the point. Right, for instance, that we get, well, from increase to decrease, if that is smoothly changed or not that smooth change, that is a sharp change. Either way, right, that we get from increase to decrease at the value of c, then we get the function is a relative maximum at the point CFC. Right, graphically it's making sense, right, still. Then the third one is, well, if f prime of x is positive on both sides of c, or negative on both sides, then the point is neither relative minimum nor a relative maximum. So which means if it doesn't change the monotonicity, in other words, that could be a cubic function, that could be a negative function power to the fifth, that we get a horizontal tangent line over here, or could be some radical functions that has a vertical line as the asymptote. It's continuous but not differentiable, that is it, but it doesn't change the monotonicity. What we get is the, at CFC, the point, right? It's neither maximum nor minimum. It's just a point that's going through it, but it didn't change the monotonicity, right? Basically, it's always increase or always decrease as going through that point. So at that point, even though it's critical number, but it is not the relative minimum and it's not the relative maximum. Right, so that is the entire thing to determine, right, if we get a minimum or maximum. And that is called the first derivative test. It's viewing the change of increasing and decreasing. Right, the next example, find the relative extrema of f of x equals x to the fourth plus 1 over x squared. Or you can use the quotient rule to find the derivative, of course, and not using quotient rule but separate it is also a good way. Right, the domain of the function is negative infinity to 0, union 0 to infinity. Right, two pieces together, that's our domain. Because, well, the denominator cannot equal 0. Right? To find f prime of x, f of x we can simplify first, that's x squared plus x to the negative 2. Right, f prime of x, that will be 2x minus 2x to the negative 3. That's x to the third, 2x to the fourth minus 2. Right, if we write a little more, that's 2x minus 2 over x to the third. That we get x to the third as a common denominator, we'll get x to the fourth minus 2. Which, if you want, you can factor the 2 out, that's x to the fourth minus 1. Which is 2 times x squared plus 1, x squared minus 1, and so on. Right, so to find the critical numbers, f prime of x equal to 0, f prime of x undefined, which f prime of x equal to 0, that's the numerator to x squared plus 1, x plus 1, x minus 1. Equal to 0. Right? We cannot have x squared plus 1 to equal to 0. We have x to be negative 1, x to be positive 1 to make this form equal to 0. Or f prime is undefined at x cubic equal to 0, that x equal to 0. But this one is not in the domain. It's not in the domain. Right, so we need to check the value. F of negative 1, that is negative 1 to the fourth. That's 1 plus 1 is 2 over 1 is 2. F of 1, since that's even function, it will be same thing. Right, the values are found. Then the last thing we will do is just the intervals. Right? Negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. For the test value, for the f prime, and finally for the function f, negative 2, negative a half, 1 half, and 2 are the appropriate value. Well, what we can see is, well, 2 and x squared plus 1 are positive. The only differ is x plus 1, x minus 1 over x to the third will fits or will affect our sign. Right, so for negative 2, we get negative 2 minus 1 over the cubic of negative 2. That is negative, 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 which will be negative. And for negative a half, that's negative 1/2, negative 1/2, negative 1/2. And negative 1/2 plus 1, that's positive. Negative 1/2 minus 1 is still negative. Negative 1/2 to the third power is negative. So we have a positive number here. And the third one we have 1/2 plus 1, 1/2 minus 1, and 1/2 to the third. We get a positive number, negative number, and a positive underneath. That we get a negative. And at the end will be similarly, that's 2 input, everything is positive, to get a positive number. Right? So to verify them, you can of course to do step-by-step work, but I'm just doing it a little fast. Right? So we get the interval of decrease, increase, decrease, and increase. Therefore, f increases on the interval from negative 1 to 0 and 1 to infinity, decreases on the interval from negative infinity to negative 1 and from 0 to 1. And that's the f of x, how it's increase and decrease. Then f, the point negative 1, 2 is a relative minimum. The point 1, 2 decrease to increase, decrease to increase is also a relative minimum. Well, which at 0 will get a vertical asymptote, so nothing would happen at 0. Right? 0 cannot be defined, so only care about it at negative 1 and at positive 1. Both of them are from decrease to increase.